And all I am is a man. I want the world in my hands. I hate the beach.
Imagine traveling to a distant galaxy. What if you could bypass the vast cosmic distances? What if there were shortcuts hidden within the fabric of space-time itself? These shortcuts, known as wormholes, have captured the imaginations of scientists and science fiction enthusiasts alike. But what exactly are they, and could they really provide a shortcut through the cosmos? Wormholes are theoretical tunnels that connect two different points in space-time. Picture the universe like a giant sheet of paper. Normally, traveling between two distant points would require traversing the entire distance across the sheet. But a wormhole would be like folding that sheet in half, creating a shortcut between the 2 points. This shortcut would allow us to travel vast distances in a much shorter time. The concept of wormholes might sound like something straight out of science fiction, but it is rooted in real scientific theory. Einstein's theory of general relativity, which describes the nature of gravity, allows for the possibility of these space-time shortcuts. While we have yet to observe a wormhole directly, the mathematics of Einstein's equations suggests they could exist. The journey into the realm of wormholes is a fascinating one, leading us to question the very fabric of the universe and the limits of our understanding. So let's embark on this journey together and explore the mind-bending possibilities of these cosmic shortcuts. The concept of wormholes can be difficult to grasp, especially when we try to imagine them in the vastness of space. To understand them better, let's use a simple analogy: a piece of paper. Imagine a flat sheet of paper. This sheet represents the fabric of space-time. Now draw 2 points on the paper far apart from each other. These points represent 2 different locations in the universe. Traveling between these 2 points would normally require traversing the entire distance across the paper. However, if we were to fold the paper in half, bringing the 2 points closer together, we create a shortcut. This fold represents a wormhole. Instead of traveling the long way around, we can now simply pass through the fold and arrive at our destination much faster. Of course, this is a simplified analogy. In reality, wormholes wouldn't be simple folds in space. They would be incredibly complex structures, potentially involving immense amounts of energy and exotic matter. But the paper analogy helps us visualize the basic principle behind wormholes. They provide a shortcut through space-time, allowing us to travel vast distances in a shorter amount of time. To delve deeper into the concept of wormholes, we need to understand the framework in which they exist. Einstein's theory of general relativity. This theory, published in 1915, revolutionized our understanding of gravity. Before Einstein, gravity was seen as a force acting between objects with mass. But Einstein proposed a radical new idea. Gravity is not a force, but a curvature in the fabric of space-time. Imagine placing a bowling ball on a trampoline. The ball creates a dip in the trampoline's surface. Similarly, massive objects like stars and planets create dips or curvatures in space-time. These curvatures are what we experience as gravity. Einstein's equations showed that space-time could be bent, stretched, and even folded. It is this folding that allows for the theoretical possibility of wormholes. Just as the paper analogy showed us a shortcut created by folding, wormholes are thought to be tunnels formed by extreme warping of space-time. They connect 2 distant regions of the universe, much like a cosmic shortcut. While wormholes are theoretically possible within the framework of general relativity, their existence remains purely hypothetical. Scientists have proposed different types of wormholes, each with its own set of challenges and complexities. One type is the Schwarzschild wormhole, named after physicist Carl Schwarzschild. These wormholes are theorized to be incredibly unstable and would likely collapse faster than the speed of light, making them impassable. Another type is the traversable wormhole, which, as the name suggests, could potentially be traversed. However, these wormholes would require the existence of exotic matter, a hypothetical form of matter with negative mass energy density. Exotic matter is purely theoretical and has never been observed. Its existence is debated among physicists, and its properties challenge our current understanding of physics. Even if exotic matter exists and could be harnessed to create a traversable wormhole, the challenges don't end there. The amount of exotic matter required would be astronomical, and the stability of such a wormhole is still uncertain.